Welcome to this comprehensive course on AI-powered observability. I'm presenting this content on behalf of SKRS channel as part of our Future Tech and AI series. Before we begin, I encourage you to subscribe to the channel and enable notifications to stay current with our technical curriculum. This program is designed for engineering teams seeking to transform their monitoring infrastructure from reactive alerting to proactive, intelligent automation. Over the next hour, we'll cover enterprise-grade integration strategies, agentic AI implementation, and production deployment patterns. Let's establish foundational concepts. Observability represents a paradigm shift from traditional monitoring. Rather than simply collecting data, observability enables deep system understanding through three fundamental pillars. First, metrics. These are quantitative measurements of system performance, CPU utilization, request latency, throughput characteristics. Second, logs, discrete event records providing contextual detail about system behavior and application state. Third, traces, end-to-end request flow visualization across distributed architectures. The challenge facing enterprise environments is data fragmentation. Most organizations operate heterogeneous monitoring stacks. Common architectural patterns include Prometheus or Datadog for metrics collection, Elk Stack or Splunk for log aggregation, and Jaeger or Zipkin for distributed tracing. This fragmentation creates significant operational overhead. It increases mean time to resolution and prevents holistic system understanding. Consider a practical example from the financial services sector. A trading platform experiences degraded performance during peak market hours. Metrics indicate elevated CPU consumption. Log analysis reveals database query timeouts. Without unified correlation, engineering teams waste critical time context switching between tools rather than resolving the root cause. The key principle here is straightforward. Effective observability requires both comprehensive data collection and intelligent correlation. Isolated data points provide visibility. Unified context enables understanding. Professional exercise for this module. Document your current monitoring architecture. Identify three distinct data sources. Quantify the operational overhead of manual correlation. Calculate your current average mean time to resolution for production incidents. This baseline measurement is critical for evaluating improvement as we progress through the course. Module summary: modern observability transcends simple data collection. The foundation of intelligent systems requires unified, contextualized telemetry. In the next module, we'll architect a solution using OpenTelemetry. If you're finding this content valuable, I encourage you to support SKRS channel by subscribing and sharing this material with your engineering colleagues. Module 2: Data Integration Architecture. Building production-grade observability requires a standardized data pipeline. OpenTelemetry provides vendor-neutral instrumentation for metrics, logs, and traces. Let's examine the architectural approach. The architecture consists of three primary components. Component 1: Data Collection. OpenTelemetry SDK's instrument application code, providing automatic telemetry generation. Component 2: Data Processing. The OpenTelemetry collector aggregates, filters, and enriches telemetry before export. Component 3: Data Export. Unified backend storage solutions like Grafana, Elasticsearch, or New Relic. Enterprise deployment follows a phased approach. Begin with a proof of concept instrumenting a single service. Gradually roll out across microservices, eventually migrate legacy instrumentation to the unified standard. Industry example: Netflix processes billions of telemetry events daily using OpenTelemetry. Their architecture achieves sub-second latency while maintaining comprehensive observability across thousands of microservices. Let's examine technical implementation. The code initializes tracing infrastructure. We configure a tracer provider, establish a batch span processor connected to our collector endpoint, and instrument application logic. This implementation provides automatic context propagation across service boundaries, enabling end-to-end request tracing without manual correlation. Quantifiable results from production deployments are significant. Organizations implementing unified telemetry pipelines typically achieve 60 to 80% reduction in mean time to resolution. One SaaS provider reduced incident triage time from 30 minutes to under 5 minutes through OpenTelemetry adoption. Professional exercise. Deploy an OpenTelemetry collector in your development environment. Configure receivers for your existing monitoring infrastructure. Establish baseline metrics for query latency and correlation time. This hands-on implementation provides practical experience with the integration patterns we've discussed. Module summary: standardized telemetry pipelines eliminate data fragmentation. OpenTelemetry provides production-ready infrastructure for unified observability. Next, we'll add intelligence through agentic AI systems. Explore more advanced integration patterns in the Future Tech and AI playlist on SKRS channel. Module 3: Agentic AI Systems. Traditional monitoring systems operate reactively, triggering alerts based on predefined thresholds. Agentic AI systems employ autonomous reasoning to understand context, investigate root causes, and execute remediation strategies. Let's examine this evolution. The architectural distinction is fundamental. Reactive systems implement rule-based threshold alerting with manual investigation. Agentic systems provide autonomous context understanding, multi-step reasoning, and automated remediation. Core components of agentic architecture include 4 elements. First, large language models providing natural language understanding and reasoning capabilities. Second, tool integration enabling API connectivity for querying systems and executing actions. Third, contextual memory maintaining persistent state across investigation cycles. Fourth, decision frameworks implementing policy-driven autonomous action within defined boundaries. Agentic systems excel in complex scenarios requiring multi-source correlation. During anomaly detection, agents autonomously query metrics databases, analyze log patterns, correlate user impact, and recommend or execute scaling operations. Case study: Google DeepMind's autonomous agents achieved 40% energy reduction in data center operations through predictive optimization and proactive infrastructure adjustments. The implementation framework demonstrates practical application. We define an observability tool interface for querying unified telemetry. The agent configuration includes capabilities for accessing metrics, logs, and traces. When executing autonomous investigation, the agent reasons through the problem space, queries relevant data sources, and synthesizes findings. The critical innovation here is autonomous reasoning. The system understands context, not just patterns. It correlates disparate signals into coherent narratives. Professional exercise. Develop a basic agentic system using LangChain or similar framework. Implement telemetry query capabilities against your development environment. Document the agent's reasoning process and decision tree. This exercise demonstrates the practical application of autonomous intelligence in observability contexts. Module summary: Agentic AI transforms observability from reactive alerting to autonomous intelligence. These systems reduce operational overhead while accelerating incident response. Next, we'll enhance precision through vector search and semantic relevance. Support our technical content by subscribing to SKRS channel for comprehensive AI engineering tutorials. Module 4: Vector Search and Semantic Relevance. Traditional search operates on lexical matching, exact keyword correlation. Vector search employs semantic embeddings to understand conceptual relationships, dramatically improving signal-to-noise ratio in large-scale telemetry datasets. The technical foundation is important to understand. Vector embeddings transform textual data logs, metric labels into high-dimensional numerical representations. Semantic similarity is computed through vector distance metrics, enabling conceptual rather than lexical matching. Production deployments utilize specialized vector databases, Pinecone, Weaviate, or Milvus, integrated with observability backends. Embedding models such as BERT or sentence transformers process incoming telemetry in real time, enabling semantic queries across billions of data points. Performance impact is substantial. Uber's observability platform leverages vector search to achieve 70% faster root cause identification. Semantic correlation automatically links related incidents across disparate services. The implementation demonstrates practical application. We initialize an embedding model, generate semantic embeddings for our telemetry dataset, build a vector index for efficient similarity search, and execute semantic queries. When querying for performance degradation in payment system, the system returns semantically similar incidents even when the exact keywords differ. The query might return results about CPU utilization, database connection exhaustion, and network latency, all conceptually related to performance issues despite different terminology. Operational advantages are significant. During incident response, security teams leverage vector similarity to correlate seemingly unrelated alerts into comprehensive attack narratives. Performance engineers identify systemic issues through pattern recognition across service boundaries. Professional exercise. Implement vector search against historical incident data from your organization. Benchmark semantic relevance against keyword-based approaches. Quantify improvements in false positive rates and investigation efficiency. This comparative analysis demonstrates the practical value of semantic search in production environments. Module summary: vector search enables semantic understanding of telemetry data, dramatically improving observability precision. Next, we'll orchestrate these capabilities into automated workflows. Share this course with your engineering team. These advanced techniques provide significant competitive advantages. Module 5: Workflow Orchestration and Automation. Enterprise-grade observability requires coordinated automation across detection, investigation, and remediation phases. Multi-agent systems orchestrate specialized capabilities through structured workflows. The workflow architecture consists of 4 phases. Phase 1: Detection, anomaly identification through vector similarity analysis. Phase 2: Investigation, semantic query execution across telemetry sources. Phase 3: Correlation, multi-source pattern recognition and root cause analysis. Phase 4: Remediation, automated response execution within defined policy boundaries. Modern orchestration frameworks CrewAI, AutoGen, LangGraph enable complex multi-agent collaboration. Each agent specializes in specific capabilities while coordinating through a central orchestration layer. Enterprise results are compelling. Microsoft Azure monitors agentic workflows reduced mean time to resolution by 50% across their global infrastructure. Autonomous investigation handles 80% of incidents without human intervention. The technical implementation demonstrates multi-agent coordination. We define specialized agents: a detection agent expert in semantic analysis, an investigation agent with distributed systems expertise, and a remediation agent focused on infrastructure automation. Each agent receives specific tasks aligned with their capabilities. The detection agent analyzes telemetry for anomalous patterns. The investigation agent correlates multi-source data to determine root cause. The remediation agent executes appropriate responses within policy constraints. The orchestration framework coordinates information flow between agents, ensuring each agent has necessary context from previous phases. Operational considerations are critical. Production deployments require governance frameworks. Policy engines define automation boundaries. Approval workflows manage high-risk actions. Audit logs ensure compliance. Human oversight remains essential for edge cases and strategic decisions. Professional exercise. Design a multi-agent workflow for a production incident scenario from your environment. Define agent roles, task dependencies, and escalation criteria. Implement a proof of concept with simulated telemetry data. This design exercise demonstrates practical application of orchestration patterns in your specific operational context. Module summary: orchestrated multi-agent systems automate complex incident response workflows. These architectures dramatically reduce operational overhead while maintaining reliability. Next, we'll address enterprise scaling challenges and production deployment patterns. Subscribe to SKRS channel for advanced automation patterns and enterprise architecture tutorials. Module 6, Enterprise Scaling and Production Deployment. Enterprise observability platforms process petabytes of telemetry data while maintaining sub-second query latency. Scaling requires careful architectural decisions across storage, processing, and AI inference layers. Scaling dimensions include 4 critical areas. First, data volume, distributed storage with time series optimization using technologies like ClickHouse or TimescaleDB. Second, query performance, vector index sharding and intelligent caching strategies. Third, AI inference, model optimization and batched processing for cost efficiency. Fourth, reliability, multi-region deployment with automated failover capabilities. Platform architecture offers 2 primary approaches. Commercial solutions like New Relic AI or Datadog AIOps provide turnkey platforms with built-in agentic capabilities. These solutions offer rapid deployment at the cost of vendor lock-in and potentially higher operational expenses. Custom implementations combine open-source components, Grafana for visualization, Pinecone for vector search, and orchestration frameworks for automation. This approach maximizes customization and cost control while requiring deeper engineering investment. Performance at scale is well demonstrated in production. Databricks' Lakehouse architecture processes exabytes of telemetry data while supporting real-time machine learning inference for anomaly detection across thousands of concurrent queries. A critical consideration: observability systems require comprehensive self-monitoring. Agent performance metrics, query latency tracking, and AI inference costs must be continuously monitored to prevent recursive failure scenarios. Production checklist includes 5 essential elements. Distributed tracing across all observability components, circuit breakers for external dependencies, rate limiting and cost controls on AI inference, comprehensive alerting on platform health, regular disaster recovery testing. Case study from the healthcare sector: a major healthcare provider implemented agentic observability for patient monitoring systems. Predictive analytics identify equipment failures before they occur. Automated workflows coordinate maintenance activities. This system prevents an estimated 200 critical failures annually, directly impacting patient outcomes and safety. Professional exercise: design a scaled deployment architecture for your organization. Define storage tiers, query optimization strategies, and disaster recovery procedures. Deploy a miniature version processing 10,000 events per second and benchmark performance characteristics. This architectural exercise prepares you for production deployment planning. Module summary: enterprise scale observability requires careful architectural planning across all system layers. Production deployments demand comprehensive self-monitoring and operational governance. You're now prepared to implement these systems in production environments. Explore enterprise architecture patterns in our complete Future Tech and AI series on SKRS channel. Capstone Project: OpenTelemetry AI Guardian Platform. Apply the complete course curriculum by building a production-ready agentic observability platform. This capstone demonstrates mastery of integration, AI orchestration, and enterprise architecture. Technical requirements include 5 core capabilities. Requirement 1: unified data integration. Implement OpenTelemetry collectors for a minimum of 2 data sources. Prometheus plus ELK stack is recommended. Demonstrate end-to-end tracing across service boundaries. Requirement 2: vector search implementation. Deploy semantic search infrastructure using FAISS or Pinecone. Achieve sub-100 millisecond query latency on 100,000 or more telemetry events. Requirement 3: multi-agent orchestration. Build autonomous investigation workflows with specialized agents for detection, analysis, and remediation. Requirement 4: production deployment. Deploy on AWS ECS or EKS or Google Cloud GKE with horizontal scaling capabilities. Implement comprehensive monitoring for the observability platform itself. Requirement 5: natural language interface. Create a semantic query interface enabling natural language incident investigation. Deliverables include 4 components: architecture documentation with detailed component diagrams, GitHub repository with deployment automation, performance benchmarks demonstrating scale characteristics, video demonstration of autonomous incident response. Share your implementation in the comments. Exceptional projects will be featured in upcoming SKRS channel content, providing visibility for your work and contributing to the broader engineering community. Core synthesis key principles. Principle 1: Unified telemetry architecture. Observability effectiveness correlates directly with data integration depth. Eliminate silos through standardized collection and correlation. Principle 2: Autonomous intelligence. Agentic AI transforms observability from reactive alerting to proactive system understanding. Invest in orchestration frameworks enabling complex reasoning workflows. Principle 3: Semantic precision. Vector search and semantic relevance dramatically improve signal-to-noise ratio in large-scale telemetry. Prioritize embedding quality and index optimization. Principle 4: Operational governance. Production deployments require comprehensive policy frameworks, self-monitoring, and audit capabilities. Automation accelerates response but requires appropriate guardrails. Principle 5: Continuous evolution. Observability platforms require ongoing optimization. Monitor agent performance, query patterns, and cost metrics to inform architectural improvements. Professional development path. This course provides foundation for advanced observability engineering. Continue developing expertise through several avenues, contributing to the OpenTelemetry ecosystem, publishing incident response automation patterns, speaking at observability and SRE conferences, building open-source agentic observability tools. These activities establish thought leadership while contributing to the broader technical community. Course completion. You have completed the comprehensive curriculum on AI-powered observability systems. You're equipped to design, implement, and operate production-grade intelligent monitoring platforms. If this course provided value, I encourage you to support SKRS channel through engagement. Subscribe for ongoing technical content. Like this video to improve its visibility. Share with your engineering colleagues who would benefit from this material. Comment with your implementation experiences and questions. Additional advanced topics are available in the Future Tech and AI playlist, including distributed systems patterns and MLOps integration. Thank you for your attention and dedication to technical excellence. I look forward to seeing your implementations and continued professional development. This concludes the course.